Hello! Last time, we proved that every nim game has a nimber and derived a winning strategy for every winning nim game. However, our discussion depends on this main theorem which we have not proved yet. The theorem states that, suppose we write n as a sum of distinct powers of 2's, then star n is equivalent to the nim game where each pile is one of these powers of 2's. We will prove this theorem in this lecture. Now the proof uses the following lemma, which we will leave as an exercise. Let p and q be non-negative integers less than 2 to the a. And suppose that our theorem holds for all values less than 2 to the a. Then p plus q is less than 2 to the a. Before we prove the theorem, we will give an illustration for the proof of the theorem. Let's consider star 7. Now writing 7 as a sum of powers of 2's, we see that 7 is equal to 4 plus 2 plus 1. So we want to prove that star 7 is equivalent to star 4 plus star 2 plus star 1. Now the proof is going to be done by induction. So here, star 2 plus star 1 is going to be equivalent to star 3 by induction. So now we want to show that star 7 is equivalent to star 4 plus star 3. The way that we will do this is by using a previous lemma. We will show that the two sides have equivalent options. So let's look at star 7. The options of star 7 are star 0, star 1, all the way up to star 6. And now let's look at the options of star 4 plus star 3. There are two types of options here. One type of options will move on star 4, and another type of options will move on star 3. So let's look at these two types separately. For the first type of options, we have star 0 plus star 3, star 1 plus star 3, star 2 plus star 3, and star 3 plus star 3. Notice that each of these is a sum of two numbers that are less than 4. So we can invoke the lemma above and say that each of these is equivalent to something that is also less than 4. And in fact, they are less than 4 if we calculate them, star 3, star 2, star 1, and star 0. And they are all distinct. So we have taken care of the options of star 7 from 0 to 3. For the second type of options, they are star 4 plus star 2, star 4 plus star 1, and star 4 plus star 0. Now in each of these, the first number is a power of 2, that's 4. But the second number is less than 4, so its binary expansion should not contain 4. So for each option, each power of 2 appears at most once in the two numbers. So we can apply induction to say that these are just equivalent to the star of the sum of these two numbers. And in this case, we do get star 6, star 5, star 4, the remaining options of star 7. So the options of star 4 plus star 3 are equivalent to the options of star 7. So they are equivalent. We can now start the proof of our theorem. We prove by induction on n. When n is equal to 1, n is 2 to the power 0, and star 1 is equivalent to star of 2 to the 0. So now suppose that n is equal to 2 to the a1 plus 2 to the a2, etc., where a1 is greater than a2 greater than the rest. We now partition n into two parts, 2 to the a1 and the rest. We let q be that second part, n minus 2 to the a1, which is 2 to the a2 plus 2 to the a3, etc. Now if q is equal to 0, then n is just equal to 2 to the a1. So star n is equivalent to star 2 to the a1, and we are done. So we now assume that q is at least 1. Since q is less than n, we can apply induction to get that star q is equivalent to star to the a2 plus star to the a3, etc. To complete the proof of the theorem, it remains to show that star n is equivalent to star to the a1 plus star q. We will prove this by showing that star n and star to the a1 plus star q have equivalent options. The options of star n are star 0, star 1, all the way up to star n minus 1. And the options of star to the a1 plus star q can be partitioned into two types. For the first case, we consider the options of the form star I plus star q, where I is less than to the a1. Now, since I and q are strictly less than n, by induction, the theorem holds for I and q. So star I and star q are equivalent to the sums of the nimpiles of their binary expansions. Now, using arguments from the last lecture, we can see that star I plus star q is equivalent to star Ri, where Ri is I plus q. As an aside, the argument that we are using from the last lecture actually assumes that this theorem holds, but we claim that we can still use it here, so you should check that there is no circular logic in our proof. And now, since we see that I and q are strictly less than 2 to the a1, we know that Ri is also less than 2 to the a1 by our lemma. So what we have are numbers r0 all the way up to r to the a1 minus 1 that are non-negative and also strictly less than 2 to the a1. We now show that these Ri's are distinct. So suppose two of them are the same, so Ri is equal to Rj for some ij. Then, star Ri is equivalent to star Rj. So star I plus star q is equivalent to star j plus star q. Adding star q on both sides, we get star I is equivalent to star j. This is using the copycat principle. So therefore, I is equal to j. And that proves that the Ri's are distinct. Now there are 2 to the a1 of these Ri's, and there are 2 to the a1 possible values from 0 to 2 to the a1 minus 1. So by pigeonhole, for each value j between 0 and 2 to the a1 minus 1, there is exactly one Ri with Ri is equal to j. So the options of this type are equivalent to star 0, star 1, all the way up to star to the a1 minus 1. We now consider the second type of options, which are options of the form star to the a1 plus star I, where I is from 0 to q minus 1. Suppose that the binary expansion of I is 2 to the b1 plus 2 to the b2 plus etc., where b1 is greater than b2 greater than the rest. Then, no bi is equal to a1. Can you see why? So then, 2 to the a1 plus 2 to the b1 plus 2 to the b2 plus etc. is a sum of distinct powers of 2. Then, starting with star 2 to the a1 plus star I, we can apply induction on I to get that this is equivalent to star to the a1 plus star to the b1 plus star to the b2, etc. We now apply the induction on 2 to the a1 plus I to get that this is equivalent to the star of the sum of these powers of 2's. And this sum is 2 to the a1 plus I. And since I is from 0 to q minus 1, the options of this type are equivalent to star 2 to the a1, star to the a1 plus 1, all the way up to star to the a1 plus q minus 1, which is star n minus 1. Combining these two types of options, we see that the options of star to the a1 plus star q are equivalent to the options of star n. So, the two games are equivalent. And that completes our proof of the theorem. So that concludes the proof that any nim game has a nimber. We will extend this to any impartial games in the next lecture.